If you had to make a list of the 6 most important pioneers in robotics, our next speaker would be on it as well. This is Roland Siegwart. Let's welcome Roland.
Well, thanks very much for this nice introduction. So it's my pleasure to speak a little bit about flying robots, which have actually had a very fast development over the last 20 years or what in robotics. But let us switch down even more than 100 years. 1907, there was 2 French guys actually coming up with the idea of quadrotors, which all of you probably know today. And then actually, exactly 100 years ago, there was actually the first one really flying up, but not very stable. What they didn't have at this time was electric motors. They didn't have actually electronic controllers, and of course they didn't have IMU, which is extremely important to stabilize this system. So this actually somewhat died out, but the idea was a long time already around. Now we started actually with quadrotor again, 100 years later, because we realized there is IMUs, small units which can actually measure accelerations and rotational speed. We have very fast direct drive motors, and I have the control unit which allow to fly this. And this was actually, to our knowledge, the first time such a quadrotor was up in the air and stably. It had even some ultrasound sensors which allowed to do collision avoidance. And it actually started a lot of movement. And you all know, meanwhile, millions of these quadrotors are sold all over the world for taking images from the air. Now, one disadvantage of these quadrotors is that they are highly inefficient. So nobody cares about a small drone being inefficient because you only probably fly 5 minutes to take some images. But if you want to carry people around with multicopters, it's probably not the best way to do. You can see here, this is the specific energy consumption, bringing a mass a certain distance, and on the other axis you have the speed. And you can see a quadrotor or a multicopter is typically about 10 times less efficient than a fixed-wing airplane. So this is the step which we said then, can we actually go to the other end? Can we actually build an airplane which can fly forever? And of course, you can, in principle. And so what we did is building a fixed-wing airplane, which was optimized on the solar power side, but also on the aerodynamics. And we demonstrated in 2008, first time that we can fly more than 24 hours. So you store all the energy which are left over during day for the night. And in 2015, we flew 81 hours. And here you can see actually a mission we did with the Earth scientists, which are actually trying to get images from these glaciers which are far out to do some imaging in this area. What you can also see, the only painful thing with this, they are pretty brittle. So they're not so easy to handle. And they need some flat ground to get off the ground. So the next mission we went to is building something which we typically call VTOL, vertical takeoff and landing, but which is still a fixed wing. And this is the result of actually starting with a student project, even in the bachelor program, and then they continued, the student team, to this system, which is a wing-only system, the minimalistic solution, 2 propellers, 2 flaps, and it can vertical take off, as you have seen, and then go over to a fixed wing mode. So with this, you can fly faster, you can cover a higher area, and you can actually fly up to about 1 hour. So it has, in the beginning, of course, more issues by controlling it, but meanwhile, it's as reliable as a multi-copter system, and it's more and more used in different applications. So if you look as a next step, what would you do? Now, up to now, these flying platforms are always foreseen to take images from the air, being as far away from structures to not actually collide with the environment. Because you are somewhat still limited with the calculation power, with the sensors you can carry around, so you have some quite important limitations. But what if you could actually fly in physical interaction? And this was our next challenge we approached. And we have in the nature wonderful examples that you can hover and in parallel actually exert forces to the environment. This hummingbird is demonstrating this, and for us it was the challenge, can we do something similar? Now, typically, airplanes, flying robots, are under-actuated. So you cannot freely choose the attitude and the direction or the movement in all directions. This is perfectly okay for flying, for taking images in the air. But if you want to exert force to the environment, if you want to approach really and get in touch with the environment, you need at least fully actuated systems, meaning in air you need 6 degrees of freedom to control, or even overactuated. And typically you end up with an overactuated system, as you can see it here, 6 propellers, but they are rotated around their central axis. So with this, you can actually generate a lot of different thrust vectors, or all the thrust vectors you imagine, which means that you can fly up and do pure rotation without flying away, or flying up, staying horizontal, and moving in XY. Of course, this is for taking images not of big interest, but as soon as you want to interact, and this is shown here as a toy example, just connect a pen, then generate the force in force control against the black whiteboard, and then move in XY in the other direction. And you can see here, we can demonstrate that we can really write on this whiteboard without a big change. We don't need a robot arm. The robot arm itself, or the flying platform, is actually a decoupled robot arm. And of course, you can do the next. We'll see some example on this later on. Now, this is omnidirectional or fully actuated systems, and sometimes very often also even overactuated. So you have potential to do a lot of different things, but at one point it's getting very difficult to control. Today we have these wonderful tools we know also from walking robots, for example, which allows us in simulation to train different policies. And what we started to do is also to train a policy of this system to open a drawer. So you do this in the simulation with enough steps and a good model. And I think it's important always you need a good model so that you can really transfer then the control. You transfer it to the real system, and you can see all of a sudden the system is capable to really do physical manipulation at height. Here, probably still a little bit of toy example, but this will allow to have much more complex applications. Now, of course, the whole system needs also the whole navigation stack on board. I don't want to go in detail, but I think it's important that we learned with flying robots also how to build up navigation in a minimalistic way. You don't typically have lasers on board. You have very limited resources, and you have to do this. And this actually pushed us to really be among the first in doing visual navigation, visual localization with feature-based localization with really limited calculation power. If you integrate this, you can then show that you can actually, only with a single camera and an IMU on board the flying platform, fly through a forest. You build from the camera a 3D map of the environment. You do online the planning, and here the robot was just tasked to fly 100 meters in one direction, and it had to do everything by itself to find its way through this forest. Now, what can we do with this physically interactive robots at the air? So you can see on the left here, people hanging on ropes. And they are doing dangerous tasks, inspection, sometimes really maintenance of chimneys, of gas pipelines. What we want is actually to replace these people, which are in a very big danger, and it's also very expensive to have them hanging on ropes, with flying platforms. And this is the platform which now our startup company developed. It's also somewhat nearly fully omnidirectional. It has some preferences, but for this it's much easier to handle. And this can then replace, you can see it can also fly somewhat in all direction, not in a full rotation, but this you don't need. It has the tools in the front which allow to be changed. So you can measure here, you measure actually the thickness of the steel tank. If there is too much corrosion, you can also in parallel measure actually the thickness of the paint which is on it. You can then also from different angles, because you need to have a different angle. And because it's overactuated or fully actuated, it's stable. There are some people trying to do this with quadrotors, some add then an arm, but you are still always at the limit of stability. It's very difficult to control because in principle, if you want to control a force against a wall, with a quad rotor, you have always to tilt in, and then you're getting at the limit of your control. So you can see here with different tools and different environments. So one of the most interesting part is this one, really grinding off, and the last one, which is actually measurement of the lightning protection systems of wind turbines, where you can do this with a drone like this in 20 minutes for one wind turbine. With human rope, it's about 6 hours. So with this, I come to the end. So I think flying platforms, flying robots, is probably was the most fast evolving market in the last 20 years, really from research to market. But however, you cannot cheat the physics. There is still some limitations. There is a lot of this urban mobility stuff, which I think is a little bit critical because they are not efficient, some of these concepts. Thanks to the pioneer work at universities, I think they have been a fast-growing business, mainly today for aerial imaging, agriculture, search and rescue, but more and more also for in physical interaction with the environment. You can see here a video of the Wingtrat drone with only one camera in 6 hours mapping the entire city of Zurich with a resolution of 3 centimeters. Only with one camera flying over the city of Zurich. There is still a fast evolvement of new technology. These systems will become much more efficient indoor, for example, also flying from in to outdoor. I think there is always an important element that you entirely design the whole system. It's not only about AI or control, it's about system design, about motors, actuators, and the whole complex task. And as we heard already in the morning, AI is a wonderful tool to help on this, but I'm pretty sure that this will not by itself solve all the issues we have for robotics in the future. Thank you.
Thanks, Roland. We have time for a couple of questions for Roland while we swap in and out laptops. And again, when you raise your hand, wave it wildly so we can see you from the stage. This one right up there.
Yep.
HDMI goes here to the left. Yes, that one to the right, thank you. So there you can see.
Just shout.
Yeah, shout.
So they will switch later. So you see.
Yes.
Come closer. It looks like it's working now. It works now? Yes. Thank you very much for all the inspiring work, you and your ASL team. So for me, this is one of the things that I think anyone in aerial robotics struggles with, is that it seems like all the essential fundamental control problems are solved. And it is very hard to convince people from outside this industry that there is a lot of fundamentals issues that we still have to tackle. In your opinion, what are some of those issues?
I think there is absolutely new issues which are coming up with this physical interaction, because there you have really more or less the same complexity or even more complex system than with all the other robots. Human robots have to interact with the environment, they have to understand the environment, they have to physically interact, they have to measure forces, they have to switch policies. And what we are working on is really also how can we actually switch policies, how can we actually make it very stable in the air, then moving from free flight towards contact with the environment and doing then very precise movement. I think there is still a lot of things to do because the next generation of flying platforms is not only flying in free air, but interacting. And we call it more or less a free flying hand in the air, which is in principle a robot, but it has no connection to whatever, but it's free flying in the air. And because it's omnidirectional, you can do whatever typically a hand can do.
Thanks, Roland.